Let's continue looking at basic Linux commands. So we've looked at this list so far up to ID. Let's continue selecting some commands that are of interest, of use, and bound to show up in your career as a Linux Unix engineer. Again, these commands are ubiquitous across the Linux sphere, so if you know it on one platform, you will be able to find your way around on other platforms, making life more flexible, much easier for you. So what else is of interest to us? Well, ID tells us information about UID, GID, etc., as we've noted. What about generating directories, creating new directories? That's a simple command, make dir. If you're familiar with DOS-MD, same thing. Creates new directories. And as a simple example, we like to make temp directories for storing temporary information. But make dir will accept, as will many of these commands, more than one directory to create on the fly. But let's go ahead and just make it anyway. So we'll make directory temp, echo the exit status, and that means it's there. So we now have a temp directory. But supposing you wanted to make multiple directories, then you would indicate as such. Let's do temp 2, 3, and 4. Echo the exit status. And now we've got temps 2, 3, and 4. So you can make directories using make dir. Let's move on. What if you wanted to remove, let's say, directories or files? Let's indicate that command as remove, or rm. There's also rmdir, but rm with the appropriate options will do the trick. Removes file or files or directory or directories. So for example, we've just created a list of directories. To remove them, we'll use the rf option, temp star, which is a wildcard. This will remove all instances of temp from the file system. So let's go ahead from our current directory, of course, not from the root of a file system. Let's lsltr, and those directories are gone. You could also remove your test files if you'd like, doing the following. Remove rf test, let's say question mark or test star would do the trick. Let's regenerate those directories, and they're back intact. Now supposing we wanted to remove those directories selectively, an optional way that the shell understands is if we indicate a range of values, such as the following, using character classes, which is a simple form of regular expressions. So temp, let's say we wanted to remove, let's take a look at what's here, perhaps 3 and 4, leaving temp 2. So 3, 4 would achieve that result. And this uses a character class. Let's try this out. Echo the exit status, and that's the wrong variable. But notice that temps 3 and 4 have been removed. Let's just note what was achieved by using this option. Removes a range of items using regular expression, or a regex. It's a simple regex, and in this case it happens to be a character class, which indicates that preceding 3 or 4 should be the characters T followed by E followed by M followed by P, with again an optional 3 or a 4. So that's one way to remove items wholesale, to save yourself some time. Now this character class that's indicated with rm isn't specific to rm. It'll work with virtually any shell command, such as ls, for example. So let's take a look. We'll remake our directories, and this will create an error regarding temp 2. However, temps 3 and 4 were made. Now what if we wanted to just enumerate the contents of temp character class 3, 4. This then enumerates just those directories, excluding temp 2. So you can use character classes with basically any Linux command to achieve the result of that command, focusing in on specific directories as opposed to wholesale. So there are wildcards, there are character classes, and other regular expressions that may be applied. A wildcard is simply a regular expression value. That means all. So that's remove. Now remove RF, be careful with it because it removes recursively. Let's just note that this removes recursively, which may not be the desired intent if you attempt to remove from the root of a file system, which again could render your entire file system unusable, unbootable, and in a sad state unless you've got some sort of backup to help you out of that jam. Now we've been executing commands all along because we know they're there, but how do you know, or how does a shell know where to find the commands that we've been running thus far? Well, there's of course a command for that. The which command searches the path. So searches current path, and will indicate the path as uppercase PATH because it's a variable. So searches current path for executable, such that when you execute a command such as cat or touch or echo or w or who, if it's not a built-in command, which will search your current path for the command. So let's take a look. Let's do a which ls. ls is aliased with the colorization enabled to bin ls. So that tells us that in bin there's actually a command or a file named ls. And indeed, it's 118,000 bytes and just over. So which tells you where in the path a command can be found. How about cat? Let's see where it's located. It's in bin as well, so it's one of those core utilities that you'll find, and it is not alias. We haven't discussed aliasing, but aliasing is simply a way of shortcutting or of executing a command with options appended, however, being able to use just the basic or bare command name to execute the command. So when we execute ls, the alias really causes the shell to execute ls with the color auto option turned on. So it's a way of invoking a process with desired options without having to reuse or retype those options each and every time. So cat is in bin. Now how do we know what our path contains? Well, we've used the echo command before. Let's use it again. So as an option we did which cat and which ls. Let's just include it between single quotes, returning their paths. Now more to this which searchability functionality. Which uses the path. If we use echo to echo the path variable, it reveals the current path. The path varies depending on who's logged in and whether or not the variable has been updated within that particular terminal or pseudo terminal. So let's try to echo the path. This is the path that's searched by which when we execute which or execute a command as the currently logged in user Linux CBT. This path differs if logged in as the privileged user root. So it's user local bin, so on and so forth, and the path is delimited by colon to indicate the different directories that are to be searched. So when we search for, let's say, cat, the which command searches the path. It searches user local bin. Let's see if there's a cat command in there. There isn't. Doesn't find it. It then searches bin. So bin cat, and then it finds it. The first hit in the list from left to right will be the process or script that is executed. So which searches the currently defined path, and your path is subject to change depending on whom you're logged in as, but there is a basic path that's made available to all users, including but not limited to user local bin, bin, user bin, not necessarily sbin or user sbin or sbin, or even the user's home directory bin. In this case for Linux CBT may be available for other users. For other users it'll simply fill in the shell for the username to the currently logged in user. And we'll see that as we create other users throughout the system. So which is a command which searches the current path for executables, which may be scripts or binaries. There's still myriad commands remaining that are worth exploration. So, for example, we've been doing some tricks with the shell, such as append redirection, output redirection. Perhaps it's worth talking about a little bit. So, redirection. Basically, when you run a command, you have the following redirections available to you. Input, and let's just indicate between single quotes. Output, as well as append, and then there's also standard error, which we use when we want to capture the error from a command. But basically, we use input, output, and append redirection when running commands. Input redirection is implicitly defined for most, if not all, commands. So when you run cat followed by a file name, for example, it's treating the file name as input. So oftentimes you don't, as a consequence, specify the less than symbol when using a command for input. However, there's nothing to prevent you from doing it. So let's take a look. Examples. Cat the contents of test.txt. Let's see what happens when we do that. Let's ensure that we have a test.txt, and we do. So when we cat test.txt, the cat process is going to accept test.txt as input, had we, or as if we specified the less than symbol, and it'll send its output to standard out, which is the screen by default. Now let's intersperse the less than symbol, and you'll note that the command runs identically. So cat, or any command followed by the less than symbol, is the same as saying the command followed by the file name. Oftentimes, when you run commands without supplying a value for standard in, the command will wait on the command line, oftentimes blinking for you to supply input. So if you type cat, for example, notice it's waiting. The cursor isn't blinking, but it's waiting for us. And that's because we've yet to supply input. So let's type, this is a test. And notice that cat simply concatenates or echoes what we've typed in. Hello world. And it dumps it to the screen. When it's complete, we'll Control D, and that echoes the process, and cat has performed as expected. So let's just note that as well. So cat space test.txt reads the file test.txt as stdin or standard input. Note, however, most commands will wait for keyboard input if no input file is specified. For example, so if we execute cat with no options, and oftentimes you can just specify a hyphen, waits on stdin for input, which means you need to supply the input from the keyboard. And then let's just note that you should use Control D to quit standard in from keyboard. That usually is the escape sequence to return you to the shell. So cat with nothing waits, and you can scribble and it simply echoes it. Control D kills it. Cat with a hyphen does the same thing. Many commands will accept a hyphen to mean accept the input from the keyboard. So let's just note cat hyphen does the same as simply cat, meaning it waits on standard in for input. Otherwise, it's understood that input is generally supplied from a file. Now, output is a different story. Output usually goes to the screen. So when you cat test.txt, notice it dumped hello world to the screen. And that is the default location for sending output to the screen. However, we can influence the direction of output by using either append, which is the bottom one here, double greater than symbols, or output redirection. Now the output redirection clobbers. So clobbers target file. The append redirection appends to target file. So some examples of this would include, for example, let's cat test.txt and let's send its output to hello world.txt. So this accepts test.txt as the file and sends it on input, that is, and sends it to hello world.txt on output. And it bypasses the screen altogether. So bypasses stdout, which is standard output. And let's just uppercase it to be consistent. So it bypasses standard out, which can be quite useful. This is where the power of Linux and Unix is felt. Now, we've catted on input here, so let's just give it something, testing, and it prints it. So let's see what we're doing here. Cat test.txt, sending it to hello world.txt. This will bypass standard out. Under normal circumstances, the output will be sent to standard out. Now, hello world.txt does not exist, so output redirection will create the file. If it does exist, it'll clobber it, meaning it zeroes it out. So now, hello world.txt, notice, is identical in byte size to test.txt. So the input file and the output file are both 12 bytes. When we cat hello world.txt, it contains 12 bytes. If we rerun the process, it clobbers the file. So instead of making it 24 bytes, it's simply 12 bytes. That's where the difference between output redirection and append redirection become apparent. So supposing we needed to grow or append to the file, the target file, that's where you use append redirection. Be very careful when using output and append redirection, in particular output redirection. Should be in memory, so this does the same, but appends to target file, which means the target file will grow as opposed to being clobbered. Let's just include that additional greater than symbol, and this will grow the file. So again, these simple techniques become quite useful over time. Now let's cat it, we'll echo the exit status, and that's not the right variable. We hit the wrong key, but nonetheless, let's lsltr. Notice that hello world.txt is now 24 bytes. And if we run the process again, it'll grow to 36 bytes and 48 momentarily. And then if we cat the contents of hello world text, it contains the 4 items. So there's input redirection, which defaults usually defaults to a file, a source file. Output redirection, which clobbers the target file. So if it doesn't exist, it creates it. And append redirection will append to the target file if it exists, or creates it if it doesn't. So appends to target file if it exists, and creates it if it doesn't. And simple proof of that is to rerun the hello world text catenation after having clobbered the file. So let's remove rf hello world.txt, echo the exit status, lsltr to be sure that it's not there, and then recat using append redirection. And then you'll see that the file is now there because it's been created as expected. So it creates it if it doesn't exist. So that's input, output, and append redirection. Now there are a number of other shell features which are of interest. 16, let's talk about pipes. So Unix pipes. Now Unix pipes allow us to connect the output stream of one command to the input stream of another command. So connects output stream of command A to input stream of command B. This is very important because, as we've mentioned, Linux and Unix, and perhaps we should call this Linux Unix pipes. It's important because, as we've mentioned, Linux and Unix commands are designed succinctly to perform or excel at the functions that they provide. So that means there are myriad commands that do different things, and they do distinct things, and they do them very well. So to be able to benefit from the aggregate or cumulative capabilities of the various commands, you need a mechanism to string them all together, and that's called piping. So, some simple examples of piping. Well, supposing you wanted to take a look at the system log file, but then look at it one page full at a time. So, we could cat var log messages, which is the main system log file, which you normally need to be the super user to read. But this will overrun our screen, even if we had a large screen, let's say 30 inches. Piping it using the pipe key to another program that excels at, let's say in this case, displaying textual information one page full at a time, solves that problem. Less is one of those programs, which we've yet to discuss. Less is a pager. It shows textual data one page full at a time. Now let's take a look which less to see where it's located. It's in user bin. That means everyone has access to it. And just to give you a sense, if you less hello world.txt, it shows it to you one page full at a time. Now in this case, the command contains just one line, so there isn't much for less to do. So it needs more to do, no pun intended. So with that said, let's less our notes file. Now notice the notes file currently occupies more than this terminal window can display. So less shows us a page full, and if we press space, it shows us another page full until the document is finished. In this case, it shows end at the bottom. So that's the usefulness of less. Less excels at displaying a page full of information at a time and nothing else. Now the log file is much larger than our notes file. But if we LSL var log messages, we'll see that we don't have the permissions to interact with the file. So this is where we need to su into the system, which is yet another command that you must know. Su switches the user. It allows you to log into the system as a different user, such as root, or if you're root, log in as another user. Right now we're logged in as root. I've su'd in. Notice that the prompt terminates with a hash mark. When you're logged in as a super user within Red Hat Enterprise Linux using the bash shell and other distributions for that matter, including Debian and SUSE, Ubuntu and otherwise, including but not limited to those distributions, they all use bash. And the super user's prompt terminates with a hash mark or a pound symbol, whereas the non-privileged user's prompt terminates with a $sign. Perhaps it should be the other way around. Well, with that said, we can now examine the contents of varlog messages, which is 204,874 bytes. So, let's cat the contents, and before we pipe it to less, notice it overruns the screen and we've lost the gist of all of the messages. So, piping it to less gives us those messages one page full at a time. And even if we extend the dimensions of the window, less is smart enough to readjust the output so we don't lose any information. So you can trust that the top line is the first message in varlog messages, and the last line is the last for this particular page. Space takes you one page full forward, and continuing with space will take you forward. B will take you back. Optionally, F will take you forward, B will take you back. And if you hold down on F or space, it just advances through the document until you see end. So that's one example of using a pipe. So pipes the output of cat, so pipes output of cat into the less program, which is a pager. Now, other usages of pipes include, for example, searching files, especially large text files, for specific strings. So, for example, let's say we wanted to cat the contents of our log messages, but we don't want to see everything. We can use grep. Now, grep is a line searcher. it'll search lines for specific pieces of text. So supposing we wanted to grep for the keyword kernel, we could grep the whole document, however big, for that particular string. So let's try to find that string using pipes. So this will search, and notice there are a number of entries that pertain to kernel. So it may still be too much for us to see in one page full, at which point we pipe it back into less. So grep kernel, and then again pipe it back into less. So parses var log messages for keyword kernel, then pipes the output to less to display one page full at a time. And you can continue to string together commands using pipes so long as what you're doing is logical with respect to how the commands work. So again, just to recap, if we grep kernel, it dumps too many lines for us to see. But if we pipe it to less, there's the first entry that contains kernel. And as we space throughout, we'll see the last entry where it reads end that contains kernel. Now it turns out that this particular file contains a lot of entries for kernel, and rightfully so. For every time we start the system, the kernel has to initialize and set up the environment, so it causes a lot of entries to be created. But that's how you use pipes. You chain together using the pipe command commands that are of interest, sending the output stream of one into the input stream of another. And in this special case of piping, standard in is redirected to the data coming from the pipe. So let's just note, when piping, std in becomes the content of the pipe for each command in the chain of pipes. And you must pipe logically, meaning send from command A to command B as you envision your data being transformed. So piping is another important technique. Yet another one is command chaining. So one of the powerful things of Bash is the ability to chain together commands. That is to run command A, followed by command B, followed by command C, etc. So let's come up with a string of things to do. We'll cat the contents of var log messages. That's one command. We can then grep, it's still the same command, the kernel line. And supposing after we've grepped kernel, we wanted to pipe into the word count program to count the number of lines that have been returned. Now this is piping, which is a form of command chaining, but not as specific as we'd like to get into. But let's just run this to show you what would happen. So instead of showing us all the lines that contain the word kernel, we now see a count of the lines. So from that document, var log messages, there are 1,846 lines that contain the keyword kernel. This is a quasi form of command chaining, but more specifically, supposing we wanted to do a number of things, such as make a new directory, let's say temp perhaps 5. Let's take a look at what's available in Linux CBT's home directory. So again, temp 5. Or since we have directories there, let's remove rf temp star. That will take care of everything. And then after we've done that, let's lsl. This is a simple command chain. Instead of typing on a separate line, we can chain with one command. Now we're in as root, so that the permissions aren't misconstrued, after we remove these, before we create the next set of directories, we'll drop the su shell. But we can certainly remove as root. So now we've performed both commands. We've removed, and then we've run an ls. But an important note about this form of command chaining is as follows. It will run either command, regardless of dependencies. So in this case, notice the second time around, there were no temp directories to remove, but we still were able to have the enumeration of the content displayed. again, just to recap, if we try to remove something that's not there, that should generate an error, causing ls to fail. But in the case of command chaining, there is no dependency. So whatever you tell it to do, it'll do. So lsl, let's go with ps, ef, and notice it does everything that you tell it to do. So one of the key things with command chaining, let's just note, command chaining is not dependent upon the exit status of the most recently executed command. This may suit some situations where you need command B to run regardless of the output or status of command A, and C to run regardless, and so on. But for other scenarios, that may not be ideal. If this is ideal, use a semicolon. Let's just note, runs both commands independently. They happen in sequence, so of course the remove RF happens first, but if it fails or succeeds, or whether it fails or succeeds, ls-l will continue to run. So that's how command chaining